Okay, in this section we're going to talk about piecewise functions. The absolute value function is a simple example of function defined by different rules over different subset of the domain. Such a function is called piecewise-defined function. The domain of f of x is equal to absolute value x, as you recall, would be from negative infinity to positive infinity. For the interval from negative infinity to 0, the function has different rule as from 0 to positive infinity. If you recall the graph of absolute value of x going from negative infinity to 0, the function would be f of x would be equal to minus x, because the graph is going down, which we're going to take a look at the figure in the next slide. And as we go from 0 to positive infinity, the function has different equation, which is y is equal to x as the graph going up. So this is the graph of that. You go from negative infinity to 0, the function is y is equal to minus x. You see the slope is minus 1. As from 0 to positive infinity, the function will change to y is equal to x. That is the graph of f of x equal to absolute value of x. As you can see, they have different values. In this example, let's consider the following piecewise defined function. They're saying that if x is less than or equal to 0, your function would have this equation, x plus 2. It's a straight line. However, at x is greater than 0, your f of x is not a straight line anymore. It's 1/2 x squared, some sort of parabola. You should be able to find the values for different numbers for this function. So f of minus 3, f of 0, f of 3, and so on can be calculated here. So let's take a look at the first one, f of minus 3. So minus 3, we have to see where it is less than 0. So f of minus 3 would be where x is less than or equal to 0. We'll assume this function here then. F of 0 also would assume the same function. F of 3 would look at this other function, f of x equal to 1/2 x to the power of 2. So if x is greater than 2, like in this case for the value of 3, we're going to substitute the value of 3 right here instead of the first one. So the first one, as we talked about, because negative 3 is less than 0, we're going to look at the first function. We substitute negative 3 into the first function, we get minus 1. 0, also look at the first function. We plug it into the first function, 0 plus 2 is equal to 2. However, the next one, 3 is greater than 0, so we're going to substitute that into second function. 1/2 times 3 squared, that give me 1/2 times 9, which is 4.5. The point minus 3 and minus 1, 0 and 2, and 3 and 4.5 are on the graph of f of x. So in this case, we have f of x equal to x plus 2 for x is equal to x is less than 0. So this is the line that we're talking about. X plus 2, this is a graph of that. Y is equal to x plus 2. This is where your y-intercept is 2 and your slope is 1. Okay, so that would be the graph before 0. Right after 0, the graph would be 1/2 x squared, the graph of this parabola here. That would be a graph of this piecewise function. In this example, we want to sketch the graph. F of x equal to x plus 1. If x is less than or equal to 2, f of x equal to 3. If x is between 2 and minus 4, I'm sorry, between 2 and 4, and f of x equal to minus 2x plus 7 if x is greater than 4. So we can easily graph y is equal to x plus 1. We all know how to graph a straight line by now, and that would be plugging points. You can do that, or use a slope intercept formula. However you want to graph a straight line at this point, that's fine. And then y is equal to 3 also can be drawn between this interval, and there's all the straight lines for all of them. And then as you can see, you can graph that. It would be right here from all the number less than 2. This would be the graph. As you can see, the intercept is equal to 1, y-intercept is 1, and slope is 1. So go up 1 unit, right 1 unit. Everybody should be able to draw the straight line by now. So this would be that. And then from 2 to 3 is y is equal to 3. That's the line. Y is equal to 3 would be a horizontal line passing through point 3. So that would be this line here. From 4 to 3, not including that, let's see how you jump here, would be minus 2x plus 7. So that would be the graph of that right there. Once again, this would be like y is equal to minus 2x plus 7. We can substitute 2 points, pick 2 points to graph this. You can let x be equal to, let's say, 4, find the corresponding value, and so on. So this would be the graph of this piecewise defined function. You can use your calculator to graph these piecewise function as well. So if you enter the equations, and you would see you get this similar same shape here, same exact shape that we did manually using our graphing calculator. Okay, if they are given the graph, we should be able to write the equation of this as well. So we're going to find the formulas for this. As you can see, we have 2 pieces here, one from negative infinity to 1. We should be able to write the equation of this line. That should be pretty easy because I know the y-intercept is 0 and the slope is 1. So I can use y is equal to mx plus b. Yes, the slope of this also is equal to 1 going down. We know the slope is minus 1. And we know the x-intercept here. I can use this x-intercept, plug it into y is equal to mx plus b to find the y-intercept and write the equation of this line. So as you can see, the equation of this line here is going to be y is equal to x. And then if we're going down, the only point I have here right now is, well, the one of the points is pretty obvious, is 3 and 0. If I use this point here, 3 and 0, and knowing the slope is minus 1 going down, I can plug it back into point slope formula. Y minus 0 equal to minus 1 times x minus 3, and you can write the equation of the second line. Or you could write it in a slope intercept form too. Either way it would work. You can write y is equal to mx plus b. You could use this formula here. You can use this point here. This point here we just said is 3 and 0. Everywhere I see x, I'm going to put 3. Everywhere I see y, I'm going to put 0. And I know the slope is minus 1. I can easily solve for b here. So 0 is equal to minus 3 plus b. So b must be equal to 3. Same result we got here. Y is equal to mx plus b. The slope is negative 1. The y-intercept is 3. So there we have the equations. So now we can write down the f of x equal to x. If x is less than or equal to 1, is equal to minus x plus 3 if x is greater than 1. The domain would be all the number from negative infinity to positive infinity. The range would be from negative infinity to 2. In this case, if you look at the graph. The next concept here is a greatest integer or step function. Now, for some reason, this program cannot display this symbol here. So everywhere you see these boxes here, from here on, that it means this little symbol here, like two vertical line. This is the symbol we use for step function. So f of a step function means is equal to x if x is an integer, or if it's not an integer, if it's like then that would be the value, the greatest integer less than x. Okay, let's take a look at some example. Once again, this boxes means this symbol here from here on. So in this case, if you want to find the value of a step function 4, okay, this 4 is already integer, so the value would be equal to 4. -5, that's integer, so the value would be equal to -5. 2.46, 2.46 is not an integer, so the step function for that would be the integer that is the greatest integer less than this value. What's the greatest integer less than that? Less than this would be 2. So 2 would be the greatest integer less than 2.46. Again, this boxes means the symbol here. Pi is 3.14. 3.14 is not an integer, so we're looking for the greatest integer less than 3.14, so that would be 3. -6.5 is not integer, so the greatest integer less than -6.5 would be -7. You can always use your calculator to find this value. Most common function key that you can look for in your calculator is this int. The command int is used for many calculators to find the greatest integer function. So as you can see, we're putting int, and then we put this value 4, -5, 2.46, pi, -6.5, and the calculator calculated what we did earlier. For 4, we come up with 4. -5 is integer, is 5. 2.46 is not an integer, so the greatest number less than this would be 2. Pi would be 3.14. We recall it would be 3, and -6.5 would be equal to -7, like we described. The greatest integer function or step function, again, this is the symbol for it. As you can see, if you were going to graph this from 0 all the way to 1, the value would be 1, and then you can enter the values or function in your calculator, and you can see the table and also the graph, and all the way from 1, 1.1, 1.2, 1.3, all the value would be 1. When you jump to 2, 2 is integer, 2 would be 2, and then 2.1, 2.2, 2.3, and all the way to 3, the value would be 2, and so on. So you can see it's like a step function, and the domain would be all real numbers, right? And the range, however, would be just the integers. Okay, not the number in between, not included. If you want to graph the function, again, this symbol is not written here, so f of x equal to, that is the symbol that the program is not able to show, so that's like these two lines there. So f of x equal to a step function 1/2 x plus 1, so we can graph that. We need to plug some points here. If x equal to 0, 0 times 1/2 is 0, so f of x equal to 1. If x equal to 1, 1/2 times 1 is equal to 1/2 plus 1 would be 1.5. 1.5 is not an integer, so the the number that we go below that would be 1 still. So if you can, as you can see, if all the way to 2 the function jumps here, and between if x equal to 2, y is equal to 2, and all the way to 3, if x equal to 3 would be 3.5 plus 1, still would be equal to 2, and so on. You can see that would be the graph of a step function. So you can also use your calculator to evaluate all that, like we mentioned, and you can see that again the domain and range. The domain would be all real numbers, and the range would be those integers only. And once again, you can confirm all this result using your calculator. Okay, this would be application problem here. Downtown parking charges a $5 base fee for parking through 1 hour and $1 for each additional hour for fraction thereafter. And then the maximum fee for 24 hours is $15. We want to sketch this. This is a step function. As you can see, with the information that we have, we can graph this. Would be from 0 to 1 hour, that would be $5, and it would jump to $1 more would be $6, and so on. And also at this rate, flat fee after that would be $15 thereafter. So this would be again another example of a step function. This is another application problem. Due to acid rain, the percentage of the lakes in Scandinavia that had lost their population of brown trout increased dramatically between 1940 and 1975. Based on this sample of 2,850 lakes, this percentage can be approximated by the piecewise-defined function. So this is what we have here. We want to find the percentage of the lake that has lost brown trout by 1950 and by 1972. So we can use the rule x equal to 1950. You can find f of 1950, substitute the value, that becomes about 12.5. So by 1950, about 12.5% of the lake had lost their population of brown trout. And in the second part, and x equal to 1972, you substitute that for f of 1972, you would see you get 43.6. So above by 1972, about 44% of the lakes has lost their population of brown trout.